A geometric sequence has a common ratio, which is a common or consistent number that is being multiplied by the previous term. And this is different from an arithmetic sequence, which had a common difference, so a common number that was being added or subtracted on. If we look at the top three sequences, we can see that they're all geometric and not arithmetic. So for the first one, 4, 8, 16, 32, 64, I see there is no common difference because from 4 to 8, you're adding 4. From 8 to 16, you're adding 8. That is not the same number. So what I do notice instead is that from 4 to 8, I am multiplying by 2. I'm doubling. And then 8 times 2 is 16. 16 times 2 is 32, and so on. Now let's go to the next one. All my numbers are negative, that's not a big deal. And I see I have negative 80, negative 40, negative 20, negative 10, negative 5, and again, definitely not a common difference because I add 40, then I add 20, then I add 10, so that's no good. But instead, I see that the numbers are being cut in half each time, which means my common ratio would be a half. Negative 80 times a half is negative 40. Negative 40 times a half is negative 20. Negative 20 times a half is negative 10. And yes, you can also see it as, oh, I'm dividing by 2 each time. But instead of division, we should always turn it into multiplication. And dividing by a certain number is the same as multiplying by its reciprocal. So instead of dividing by 2 over 1, you're multiplying by 1 over 2. And finally, let's look at the last one. Negative 2, 6, negative 18, 54, negative 162. So the fact that I see that my signs are changing from negative to positive, I know that my common ratio is going to be negative. That way I get that changing of the signs. And here I see to go from negative 2 to 6, I'm multiplying by negative 3. And then let's just see if it works for the rest of them. 6 times negative 3 is negative 18. Negative 18 times negative 3 is a positive 54. 54 times negative 3 is negative 162. That's perfect. That works. So all three of these sequences did not have a common difference. Instead, they had a common ratio, and that makes them geometric. If something is geometric, then we can use an explicit formula. And that explicit formula is Tn, which is the number in the sequence, is equal to A1, the first term, times R, which is the common ratio, to the power of n minus 1. Now I'm just going to do an example to see where this formula is coming from. So I'm going to use a simple geometric sequence starting with 3 to 6, 12, 24, 48, and so on. And I can see that my first term is 3, and I am multiplying by 2 each time. And I'm also going to write down the position number. So 3 is the first term, 6 is the second, and so on. And I'm going to check to see, to get a certain number, how many times have I multiplied by 2. So to get to 6, which is the second number, I have multiplied by 2 one time. To get to 12, which is the third number, I've multiplied by 2 two times. To get to 24, which is the fourth number, I've multiplied by 2 three times now. And to get to 48, which is the fifth number, I've multiplied by 2 4 times. So to get to any number, you're multiplying by that common ratio 1 less than the position number you're in. So for the fifth term, I multiplied by 2 4 times. And I multiplied 3 by 2 4 times. So if I wanted the 11th number, I would be multiplying by 2 10 times, 11 minus 1 times. So let's try to set up that explicit formula for this specific sequence. So my first term is 3, and I'm multiplying by 2 n minus 1 times. And because you're multiplying by the same number a certain number of times, that's what makes it exponential. That's why you have an exponent. If I'm multiplying 2 by itself 4 times, I can write it as 2 to the power of 4. So if I'm multiplying that common ratio by itself n minus 1 times, I can write it as 2 to the power of n minus 1. So let's try this out in our first actual example, and we are going to graph the sequence just to visualize it, see that exponential connection a little bit, and then we'll write the explicit formula. So anytime you want to graph, of course, we should write our scale first. X is going to be the position number, and Y is going to be that number in your sequence. Now, I am going to write the position number, so for the sequence 3, 6, 12, 24, 48, which is the sequence we actually just wrote out, the first number is 3, the second is 6, and so on. So I'm going to go ahead and plot those points. The first number is 3, and yes, our scale is very large because we are going to continue our sequence. So we kind of just estimate it. It's very close to the x-axis. The second number is 6, again, very tiny. 12, 24 is kind of halfway. 48 for the fifth number is almost at 50. And if we continue this, just to get our sketch a little better, 48 times 2 is 96. So that will take us to almost 100. If I multiply 96 by 2, I get 192 for the seventh term. So that takes me close to 200. If I double that, I get 384 for the eighth number, which takes me almost halfway, or a bit past halfway, between 350 and 400. And if I double that one more time, I get 768 for the ninth term, which puts me approximately here. And then one more time, maybe for the 10th number, if it fits, it takes us to almost, or a bit over 1500, which doesn't fit on our grid. So here's what we have. You can see that exponential growth because definitely not linear. It is doubling each time, which makes it exponential. And let's just write that equation. Tn, so any number in the sequence, is the first number times our common difference of 2 to the power of n minus 1. And you know what? Let's actually use this formula and try it out. Let's say I want the 12th term. That would mean n is equal to 12. So let's use the formula. 3 times 2 to the power of 12 minus 1. I'm going to just clean it up, and by that I mean clean up the exponent. So what I'm actually evaluating is 2 to the power of 11. So make sure you are doing BEDMAS here. Okay, we know in BEDMAS exponents come first, so don't do 3 times 2 to give you 6 and raise that to the power of 11. No, we have to do 2 to the power of 11 first, which is 2048, and then we can multiply that number by 3, and we get 6144 for the 12th number. So that's how you can use your explicit formula, and you can find any number. It can be the 100th number, the millionth number. You can do it because you have this formula. So it's very easy to use. All right, let's try another example where I don't actually give you the entire sequence. So determine the explicit formula for the geometric sequence. So we know we're going to use our new explicit formula that has a common ratio of 1/3, and T5 is 9. So I'm going to look at this important information and start with the common ratio. So that means R is 1/3. And for T5 equals N, that just means that the fifth number is 9, which also means N equals 5. So let's take that common ratio and plug it into our general formula. So we don't know A1, but we know that R is 1/3. And then it will be to the power of n minus 1. And I clearly need to figure out the first term, so I'm going to use the only other information I have, which is that the fifth number is 9. So instead of Tn, I'll put 9 for the number in the sequence. And then instead of n, I will put 5. So 5 minus 1. And I will clean that up. So A1 times 1/3 to the power of 4. And now I can evaluate that. I'm going to do 1/3 to the power of 4, and I get 1/81. Now, I want to isolate for a1, and a1 is attached to that fraction by multiplication. Now you can divide both sides by 1 over 81, but that looks a little messy. So instead of dividing by a fraction, you can just multiply by its reciprocal, which is 81 over 1. And whatever I do to one side, I will do to the other. Now the reason this works is because if I do 1 over 81 times 81 over 1, I would get 81 over 81, which is 1. So I've gotten rid of that fraction, and all I'm left with on the right side is a 1. And when I multiply 9 by 81, I get 729. So now I know my common ratio from the start. I know my first term because I just solved for it. So I can write my explicit formula. Tn equals, the first number is 729. The common ratio is a third to the power of n minus 1. And there it is. Now in this scenario, I gave you a common ratio and I gave you a single number. Now sometimes I won't give you a common ratio, I'll just give you two terms, which means we have to find the common ratio and we have to find the first term. So let's look at this next example. We know it's a geometric sequence. The fifth number is negative 512 and the ninth number is negative 131,072. So we know this isn't linear, so we can't use our slope formula because it says geometric, so don't fall into that trap. The only thing I can really think of right now is to sub these numbers into the formula and see where that takes me. And just like with the arithmetic sequences, I am going to put the number that is later in the sequence first. So I'm going to put T9 before T5. So for T9, I know that my number is negative 131,072. That's equal to A1 times R to the power of 9 minus 1, n minus 1. And then I'll do the same thing for the fifth number. And my fifth number is negative 512. And that's equal to A1 times R to the power of 5 minus 1. And I'm just going to clean up those exponents, and then I'm going to do something very similar to elimination. So negative 131,072 is equal to A1 times R to the power of 8, and then negative 512 is equal to A1 times R to the power of 4. Now, I know that I can't subtract these lines because A1 R to the 8 and A1 R to the 4 are not like terms, so I can't subtract them. Instead, I'm going to divide. If I divide negative 131,072 divided by negative 512, I'm going to get positive 256. When I do A1 divided by A1, that's 1, so they're gone. They're not my problem anymore. And when I do R8 divided by R to the 4, I know that from my exponent rules, if I have the same base and I'm dividing, I'm just subtracting my exponents. So this would be R to the power of 4. Now we know how to deal with it if it had been R squared, I'd square root both sides. But based on the same idea, if something's to the power of 4, I can take the fourth root of my numbers. Now there's two different ways you can do this depending on your calculator. Some calculators let you take the fourth root, so it would look something like this, and that would cancel out that exponent. But some calculators don't have that, so another way you can do this, if you can't take the fourth root, is raising both sides to the power of a quarter. And the reason that works is because I know from my power to a power rule that if I have two exponents, I can just multiply them, and 4 times a quarter is 1, so I've solved that problem, and whatever I do to one side, I do to the other. So regardless of what method you use on your calculator to do this, you are going to get 4. Now, if you're taking an even root of something, the fourth root, the sixth root, the square root, you have to remember that there are always going to be two options, a positive and a negative. So on your calculator, if you take the fourth root of 256, it will tell you it is 4. But you have to know it's positive or negative 4 because 4 to the power of 4 is 256, but negative 4 to the power of 4 is also positive 256. So we do have two options we have to consider here. And now that I have my common ratio, I'm back to the previous example. I'm just going to sub it into one of my formulas. So I'm going to use the fifth term. So negative 512 is equal to a1 times positive or negative 4. We don't know, so we have to use both, to the power of 4, which is that 5 minus 1. Now you can do this separately and treat 4 and negative 4 as two separate equations, or you can do it all at once. It's up to you. But I know whether I do 4 to the power of 4 or negative 4 to the power of 4, it's going to be positive both ways. So when I evaluate that, I get 256. Now, if my exponent had been, let's say, 3 or 5, something odd, I would have a positive or negative number as my option. So I would have two possible A1 values. But now I'll divide both sides by 256, and I get negative 2 for my A1. And now we can write our explicit formula. Tn equals the first term, negative 2, times r, and you have to show me both options, so positive or negative 4, to the power of n minus 1. And one thing I want you to know is that you're not adding 4 or subtracting 4, you're still multiplying by that. It's just it could be positive or negative version. All right, so the last example is the exact same as the one we just did, except I wanted to see what happens when you have an odd exponent that you have to take the root of. So if you'd like, you're more than welcome to pause the video and try it out on your own right now. Otherwise, I am just going to start. So the fourth term is 120 and the seventh is 15. So I'm going to start off by writing and plugging them into my equation. And again, I'm going to start with the seventh term first, just so that when I do my elimination and I have to subtract my exponents, I can do 7 minus 4 instead of 4 minus 7. That way I can deal with a positive exponent instead of a negative one. So I'm going to do 15 equals a1 times r to the power of 7 minus 1, and 7 minus 1 is 6. So I'm just going to jump a step here. And then 120 equals a1 times r to the power of 4 minus 1, and 4 minus 1 is 3. And notice here, the higher exponent is on top, so I'm happy. Yes, when I do 15 divided by 120, I'm going to get a fraction, but that's okay. We can deal with that. So I'm going to divide my two lines, and when I do 15 divided by 120, the fraction would be 15 over 120, but that will reduce, and I'll reduce it in a minute. And then a1 divided by a1, that's 1, so it's gone. And then r to the 6 divided by r to the 3 means I do 6 minus 3, which is 3. Now I'm going to clean up the 15 over 120 because it reduces to 1/8, which is a lot nicer to deal with. And now I'm going to take the third root of both sides, or raise both sides to the power of 1 over 3, whatever works better for you. Now, when I take the third root of 1 over 8, I'm going to take the third root of 1 and the third root of 8. So the third root of 1 is 1, and the third root of 8 is 2, because 2 to the power of 3 is 8. So that means my common ratio is a half, and it's not plus or minus. And this is why I wanted to do this example, just to show you if the exponent is odd, when you're taking the root, there's only one option. It's either positive or negative, depending on what you're rooting. Okay, and now we can take this 1/2 and plug it into either equation. I'm going to plug it into the fourth term. So 120 equals a1 times a half to the power of 3, so that 4 minus 1. I will clean up the half to the power of 3, which is an 1/8. And then to get rid of this, I don't want to divide both sides by 1 over 8. Instead, I'm going to multiply both sides by the reciprocal. So that when I do that, and I do 120 times 8, I get 960 for my first term. And there's only one option here, so my explicit formula is Tn equals the first term times the common ratio to the power of n minus 1. So it's really important, if when you do your elimination, if you get an even exponent, you will have that plus minus for the ratio, which can also mean you have two options for your first term. But when it's an odd exponent, it's only one version you have to worry about.